Welcome to AP Biology, topic 2.3, cell size. My name is Paula Dunger, and I teach at Christ Church Episcopal School in Greenville, South Carolina. Have you ever wondered why cells are typically small and why we don't see giant unicellular organisms roaming the planet? Well, we're going to explore why that is in this lesson and the role that the surface area to volume ratio of cells plays in that cell size, as well as how that ratio is determined. So cells are typically small because moving materials such as nutrients and waste in and out of cells gets more challenging the larger the cell is. And so I want to walk you through a mini demonstration that I performed at home to illustrate how the size of the cell can impact its efficiency in transporting materials across its surface. So in figure 1, you see 3 various size cubes that I cut from beets, which are root vegetables, as shown in figure 1. And these cubes are going to represent 3 hypothetical cube-shaped cells with sides 0.5 centimeter, 1 centimeter, and 2 centimeters in length. And I left these cubes in this dish, and then I poured bleach over them to cover them completely, and I let them sit for 30 minutes to soak. And I used bleach because the beet cubes will turn white when exposed to the bleach, so it would be easier for me to observe how much of the bleach was able to move throughout each cube. So you ready to see the results? Let's check it out. So since there was a higher concentration of bleach outside the cubes, bleach was able to move across the surface of each cube, as you can see here by the white coloration of each cube. But I was curious how much bleach actually was transported throughout the entire cube. So I cut each cube in half, and this is what I saw. So each cube had a different amount of bleach after the 30 minutes, and the smallest cube had 96% of its total volume containing the bleach, compared to only 39% of the larger cube containing the bleach. So the smaller cube was more efficient at allowing the bleach to enter, as shown by that higher percentage of its total volume that contained the bleach. So cells need a sufficient amount of surface for exchanging materials with its surrounding environment. And we can quantify the amount of surface available for materials to move by calculating the surface area of the cubes in this case. The surface area of a cell is defined as the amount of surface covering the outer part of the cell. But it's not only about the surface area. We also have to consider the volume of the cube, or the amount of space that the entire cube or hypothetical cell takes up. By looking at the relationship between surface area to volume, we can get a better indication of the efficiency of that cell at moving materials across its surface. The larger the ratio, the more efficient the cell would be. So the formulas for surface area and volume of a cube, as well as for other shapes like cylinders and spheres, can be found on the AP formula sheet on AP Central. And I have 3 cubes that are not drawn to scale, but they're going to represent our beet cubes that were used in the demonstration. So I'm going to calculate the surface area and volume for the smallest cube to show you how to apply these equations. So the surface area of a cube is 6 sides squared. We have side squared of one face, and there's 6 faces to the cube. So we're going to multiply our side squared by 6. So we have 6 times 0.5 centimeters squared. So 0.5 times 0.5 is 0.25 centimeters squared, and we'll multiply that by 6 to get a surface area of 1.5 centimeters squared for our small cube. And I filled that in the table for us. The volume of the cube is side cubed, so we have 0.5 times 0.5 times 0.5 will give us 0.125 centimeters cubed. And now to set up the ratio of surface area to volume, we're going to put 1.5, the surface area, in the numerator, and then we'll put the volume of 0.125 in the denominator, and that gives us a surface area to volume ratio of 12 to 1 for our smallest cube. So I'm going to ask you to pause the video now, calculate the surface area and the volume and the ratio for the 1 centimeter and the 2 centimeter cube, so we can see how size influences this ratio as a cell gets larger. When you have your answers, just press play and we'll check your work. Okay, so let's see what you have. For this 1 centimeter cube, the surface area is 6 centimeters squared, and the volume would be 1 centimeter cubed. So when we set up our ratio of surface area to volume, we get 6 to 1 as our ratio for our 1 centimeter cube. For our 2 centimeter cube, should have gotten surface area of 24 centimeters squared, and a volume of 8 centimeters cubed. So when we set up our surface area to volume ratio, we get 24:8 or 3:1. So if we look now at the trend, as the cells get larger, as our cubes got larger, the surface area to volume ratio decreased. Our smallest cell had a ratio of 12:1 compared to the largest cell with a ratio of only 3:1. So smaller cells typically have higher surface area to volume ratios and therefore are more efficient at exchanging materials with the environment. And so if you think of our cube, if our smallest cube was the real cell, it would have been able to supply its internal demands of taking in oxygen and nutrients if this was a real cell, as well as removing waste and CO2 and heat. The smaller cell would have done a lot better for itself compared to our larger cell. Because as the cell increases in volume, the relative amount of surface area decreases, making it difficult for larger cells to meet those demands. And so these limitations are going to restrict cell size and shape. And I will share with you some examples of modifications that cells and organisms have to overcome this challenge in the second lesson for this topic. Scientists can use visual representations to represent relationships within biological models, including mathematical models. So let's take a look at an AP question. Below is a diagram of a cell increasing in size. Which of the following graphs best represents the effect of the cell's increasing size on its surface area to volume ratio? So I'm going to ask you now to pause the video and select your best choice and then press play and we'll see what we have. Okay, so the best representation of this relationship is D. As the length of the side of a cube-shaped cell increases, the surface area to volume ratio decreases. Some key takeaways from this lesson are smaller cells typically have a higher surface area to volume ratio and are more efficient at exchanging materials with the environment. The surface area to volume ratio can affect the ability of a cell or organism to obtain necessary nutrients, eliminate waste, and acquire and dissipate thermal energy. We also practice using formulas that can be found on the AP formula sheet for surface area and volume of a cube. And then we use that calculated surface area to volume to determine the ratio. Thank you for watching, and I hope this video is helpful. And if you need more time, just rewind.